Write your name and seat number in the chat box. So yesterday we completed this Raoult's law. I will revise the Raoult's law because 2-3 students called me, sir, we didn't understand this Raoult's law. So I will explain again this Raoult's law and I will continue the next part. So Raoult's law is related to the two vapor pressures are there, partial vapor pressure and another one is vapor pressure of a pure component. There are two, it is the relation between the partial vapor pressure and the vapor pressure of any pure component. So what is this statement? I will explain first. This according to this Raoult's law, partial vapor pressure, remember there are two vapor pressures. One is a partial vapor pressure and another one is only the vapor pressure of the pure component. So this partial vapor pressure of any volatile component, if there are if there are two volatile components or more than two volatile components, we have to take any volatile component of the solution. You know, solution is prepared by the mixture of solute and solvent, and this solute and solvent may be solid, liquid or gas. So the partial vapor pressure of any volatile component of a solution, remember, it may be a solute part or it may be solvent part, is equal to the vapor pressure of pure components. Whatever the pure component which is present in a solution, partial vapor pressure is equal to the vapor pressure of the pure component and its mole fraction. So this relation clearly indicates this P1 is the partial vapor pressure of any volatile component is equal to P01. It is the vapor pressure of the pure component. It may be solute or it may be solvent, and its mole fraction. If X1 is solute and X2 is solvent, so P2 is another volatile component, vapor pressure of another volatile component. P02 is the vapor pressure of pure component and its mole fraction. So here P is a partial vapor pressure, P2 is a partial vapor pressure of component 2, and P02 it is the vapor pressure of the pure component. So don't make confusion between this partial vapor pressure and vapor pressure. So if you understand this Raoult's law, then according to this Dalton's law of partial pressure, what is this Dalton law of partial pressures? Means total pressure is equal to the partial pressure of all the components. This is a Dalton's law. So it is a P is equal to P1 plus P2. Just it is addition of the two components. After this addition, you know this is a mole fraction is always equal to 1. The mole fraction of the solute or mole fraction of the solvent, if X1 is solute and X2 is the solvent, is always equal to 1. In 11th standard, this expression is already shown. So this reference, it is from the 11th standard. X1 plus X2 is equal to 1, remember. So if X1 plus X2 is equal to 1, automatically this X1 is equal to 1 minus X2. So this value 1 minus X2 we are putting in this equation. See, in this equation we are putting the value of X1. So P01 we have to multiply it. P01 into 1 it is P01. P01 into this X2 it is minus P01 into X2, and this plus as it is kept. So after solving this equation we will get the P is the total partial pressure of the solution is equal to P01. P01 it is the vapor pressure of component 1, pure component 1, and P naught 2 is the vapor pressure of component 2 into 2. By rearranging or solving this equation, we will get the equation 2.4, and this is a Raoult's law equation, remember. So this part is yesterday I completed, and 2-3 students also told me, sir, we didn't understand this graph. So I request all the students, this graph is not actually asked for exam. So no any question will be asked on this graph, but only we have to remember uh, these graphs are, means the graphs of vapor pressure and mole fraction are always the straight line. Means the graph of P naught 1 x1, the graph of P naught 2 x2, and the graph of total pressure is always a straight line. If one MCQ will be asked, they will not ask to draw the any graphs, so don't take any tension about these graphs. Always remember the graph of P1 versus X1 is straight line, then P2 versus X2 is also straight line. The graph of total pressure is versus X2 is always straight line. This ideal solution, non-ideal solution, the conditions also I explained yesterday. What is mean by ideal solution, non-ideal solution, and colligative properties parts is already started. So once again, I am explaining you the colligative properties. It is a Greek word. Colligative means collective properties of the solutes only. These properties depend upon the number of solutes, not depend upon the nature of solute. So number is very important in colligative properties. There are 4 colligative properties. Number 1 is vapor pressure lowering. Number 2 is boiling point elevation. Elevation means increase in boiling point. Number 3 is freezing point depression. Here depression means decrease in freezing point. And number 4 is osmotic pressure. So remember these all colligative properties, because these colligative properties can be asked for 1 mark, right? Any 2 colligative properties or write all the colligative properties. So first we will discuss the vapor pressure lowering. Before this vapor pressure lowering, we must know what is meant by vapor pressure. So vapor pressure, as the name suggests, vapor and pressure, it is the pressure exerted by the vapors on the surface of the liquid when the vapors and liquids are at equilibrium, remember. So this definition is given here: when a liquid in a closed container is equilibrium with its vapor, the pressure exerted by the vapors means the pressure of the vapors where on the surface of the liquid at a given temperature, it is called as vapor pressure. So why this vapor pressure is lowered? I will explain. Some experiments are shown when the non-volatile solute is dissolved. Now remember, this is a non-volatile solute which cannot be evaporated. When a non-volatile solute is dissolved in a liquid solvent, what happens? The vapor pressure of the solution becomes less. If the non-volatile solute is not added, the vapor pressure of the pure solvent is higher. But when non-volatile solute is added in the solution, its vapor pressure decreases. Why this is happening, I will explain with this diagram. See, in this diagram A, we will see this figure A and B. There are 2 figures. In the figure A, we can see this is a beaker. In the beaker, pure solvent is taken. This is shown with blue colored dots. This is a surface of the pure solvent. And in the figure B, we can see the solvent is there, but the non-volatile solute is added in this. This is a solution. This is a pure solvent. This is pure solvent, and this is a solution. Which solution? Solution of pure solvent plus this green colored non-volatile solute is added. So what will happen? This in this diagram, this surface is completely available for evaporation. So this surface is completely available for evaporation. So this pure solvent will be evaporate fast, and so its vapor pressure will be more. Pure solvent having the more vapor pressure than the solution containing non-volatile solute, because see, the surface area is completely not available because this surface is blocked by some non-volatile solutes are there. So it will not evaporate. See, the dots are also shown here, 1, 2, 3, 4 dots only shown, means these are the vapor particles, and in this diagram here we can clearly see the vapor pressure will be more because evaporation is more, and in this figure B vapor pressure is less because entire surface is not available for evaporation. So always remember the vapor pressure of pure solvent is always higher than the solution containing non-volatile solute. This is the explanation is given here why the vapor pressure of the solution containing non-volatile solute is lower than the pure solvent. The reason is same, because here complete surface is available for evaporation, and here complete surface is not available for evaporation. So this is explained here. So this is called as a lowering in, this results in lowering in vapor pressure. Lowering of vapor pressure means decrease in vapor pressure. So vapor pressure will be decreased when non-volatile solute is added. Simply we have to remember why the lowering of vapor pressure takes place, because when the non-volatile solute is added in the pure solvent, the vapor pressure will be lowered. So remember, solute is a non-volatile, it does not contribute to the vapor pressure of the solution. So vapor pressure of a solution is equal to the vapor pressure of the solvent only. Remember this thing, vapor pressure of a solution, this solution means it is a mixture of non-volatile solute plus solvent. See, vapor pressure of a solution is equal to only the vapor pressure of the solvent, because solute does not contributes to the vapor pressure. So this is called as lowering of vapor pressure. Vapor pressure lowering means decrease in vapor pressure, and this decrease is due to the addition of non-volatile solute. I think you understand this colligative property. So mathematically, the lowering of vapor pressure is described as this equation. If P01 here, delta P is lowering of vapor pressure, remember. It is also called as a change in vapor pressure, or it is also called as a vapor pressure lowering. Delta P is vapor pressure lowering is equal to the this P01, it is the vapor pressure of pure solvent, and P1 is the vapor pressure of the solution containing non-volatile solute, remember. So delta P is equal to P01 minus P1. P01 is always higher than P1. It is the vapor pressure of the pure solvent, and this is the vapor pressure of the solution containing non-volatile solute. So this equation delta P is equal to P01 minus P1 is a lowering of vapor pressure. Then we are coming to another Raoult's law. This Raoult's law is related to the solutions of non-volatile solute. You know, this Raoult's law is related to only the volatile components. It is not related to non-volatile solutes. So we already discussed about this Raoult's law. It is the relationship between vapor pressure of the first Raoult's law. Just I explained that Raoult's law was related to the partial vapor relation between partial vapor pressure and vapor pressure, but this Raoult's law is related to the vapor pressure of the solution and vapor pressure of the solvent. Now the concept is clear. Vapor pressure of the solvent is always higher than the vapor pressure of the solution containing non-volatile solute, because non-volatile solute disturbs the solvent to evaporate. That's why its vapor pressure is less, and vapor pressure of the pure solvent is always higher. So if these two concepts are clear, then I will start this Raoult's law for solutions of non-volatile solutes. Again, we have to take the solution and solvent here. So solution contains non-volatile solute. In a solution non-volatile solutes, the law is only applicable to the volatile solvent, remember. So this law is not applicable to the solute which is a non-volatile. This law is only applicable to the volatile solvent. And this law states that vapor pressure of a solvent, now see, vapor pressure of a solvent over the solution means vapor pressure of the solution containing non-volatile solute. This word can be written like this: vapor pressure of a solvent over solution means vapor pressure of a solution, and this solution containing non-volatile solute is equal to the vapor pressure of pure solvent multiplied by its mole fraction. Come to this equation, then we will understand. Say this P1 indicates the vapor pressure of the solution, and this solution is having the non-volatile solute is equal to the vapor pressure of the pure solvent multiplied by its mole fraction. So X1 is the mole fraction of P1. P1 is here uh, pure solvent, and P1 is the solution containing non-volatile solute, remember. So this is a Raoult's law. According to Raoult's law, we are writing this. By this expression, we can write the Raoult's law. So P1 is what? P1 is the vapor pressure of the solution is equal to, it is the product of vapor pressure of the pure solvent and its mole fraction. We can prepare this law also. So again, we are taking the binary solution. Yesterday I explained what is mean by binary solution. Means a solution containing two liquids. So again, we'll take two liquids. So it containing one solute, binary solution containing one solute. X1 plus X2 is equal to 1, and this is a mole fraction. From 11th standard I taken this concept. Again, X1 is equal to y minus X2. All this is explained in previous Raoult's law. So P1, according to this Raoult's law, P1 is equal to P01 into X1. This same equation I have taken here, putting the value of X1 in this equation. So P01 into X. This is same expression like previous Raoult's law. So only one change is there. By rearranging this equation, by rearranging this equation, we get P01 minus P1. Thus, this is only shifted to this left hand side. So P01, clearly we can see this P01 into 1 is P01. It is when it is multiplied with X2, P01 into X2. So this P01 minus P1. P01 को हमने कॉमन निकाला है. देखो P01 minus P1 is equal to P01 into X2. This is a expression for this Raoult's law, but you know, this is a delta P is equal to P01 minus P1. This is a lowering of vapor pressure. See, delta P is a lowering of vapor pressure is equal to P01. It is the vapor pressure of the pure solvent, and P1 is the vapor pressure of the solution containing non-volatile solute. So, so this is the delta P is equal to P01 minus P1. Hence, but here P01 minus P1 is equal to putting this value in this equation. So delta P is equal to P01 into X2. This value, this Raoult's law value, it is substituted in lowering of vapor pressure. So we get this equation 2.6. So 2.6 indicates what? Delta P is equal to P01 into X2. What is delta P? Delta P is lowering of vapor pressure. P01 is what? Vapor pressure of the pure solvent, and X2 is what? It is the mole fraction of the component, any component. It is the mole fraction of any component. So delta P equation 2.6, this is equation 2.6, shows that delta P depends upon the X2, where X2 is what? That is the number of solute particles. And you know, if the delta P is depend upon the X2, it is a colligative property, because colligative property is depend upon the number of solute particles and not depend upon the nature of solute particles, remember. So this is a colligative property is proved here. So this is a Raoult's law for solution of non-volatile solutes. At your home, go through this equation. Then the next point is relative lowering of vapor pressure. Now you understand what is mean by lowering of vapor pressure. So relative of lowering vapor pressure we can easily understand. Before this relative lowering of vapor pressure, again I am coming to the lowering of vapor pressure. Lowering of vapor pressure is a delta P. Delta P is nothing but this one, P01 minus P1. P01 here vapor pressure of the pure solvent, and P1 is the vapor pressure of solution containing non-volatile solute. The P01 is always higher than the P1 because here the non-volatile solute does not contributes to the vapor pressure. So already you know about this delta P, but relative lowering of vapor pressure is nothing but delta P upon P01. You know this delta P also, you know this P01 is also. So we can prepare the definition, what is mean by relative lowering of vapor pressure. So it is the ratio of lowering of vapor pressure to the vapor pressure of the pure solvent. So delta P, this is the value of delta P, P01 minus P1, and this P01, this is equation number 2.7. This equation is a relative lowering of vapor pressure, but you know, according to this Raoult's law, delta P is equal to P01 into X2. Just we derived this equation, delta P is equal to P01 into X2. This is from Raoult's law. So this P01, if it is divided, it is come to this side, it will be divided, delta P into P01 is equal to X2. So we can put this value delta P upon P01 into X2 in this equation, in the above equation. So delta P divided by P01 is equal to P01 minus P1 divided by P01 is equal to X2. So this X2 only it is substituted in this equation, equation number 2.7. So X2 it is nothing but relative lowering of vapor pressure is equal to X2, where X2 is the mole fraction, remember. It is the mole fraction of the solute, that is number of solute particles in the solution. So again this relative lowering of vapor pressure is also the colligative property. So for the board examination, the question will be asked, why relative lowering of vapor pressure is a colligative property? Explain. So if this question is asked for 2 marks, we have to write all these things and we have to derive this delta P upon P01 is equal to X2. This expression indicates this is a relative lowering of vapor pressure is equal to X2, and X2 is nothing but mole fraction of the solute. That is, mole fraction means it is a number of solute particles in the solution. So this sentence is very important. We have to write this sentence. If you didn't write this sentence, you will lose your half mark, because this X2 is important, and what is this X2 we have to write. So relative lowering of vapor pressure is a colligative property because it depends upon the number of solute particles and then not nature of solute particles. Then I'm coming to this expression is asked for 2 marks. Derive the relation between molar mass of a solute from vapor pressure lowering. Now you are familiar with this vapor pressure lowering, relative lowering of vapor pressure. What is vapor pressure? Why the vapor pressure of the pure solvent is more? Why the vapor pressure of the solution containing non-volatile solute is less? So it is very easy to derive this expression. Now you know this. You know the expression for lowering of vapor pressure. You know the expression for relative lowering of vapor pressure. We will take this equation. Yes. The relative lowering of vapor pressure is equal to mole fraction. Just I derived this expression. Relative lowering of vapor pressure is equal to the mole fraction. This equation. See, delta P upon P naught 1 is equal to X2. This equation just I derived this equation. So mole fraction of a component of a solution is equal to its moles divided by total number of moles in the solution. I will coming to this one. Say if this is a X2, X2 indicates the mole fraction. Mole fraction is nothing but number of moles. See, I will explain what, because in 11, this is 11 standard part. X2 is the mole fraction of a component, any component. It may be solute or it may be solvent. So what is this mole fraction? I will explain, because many students forgot about this mole fraction. So mole fraction is what? X2 is equal to N2 divided by N1 plus N2. Here N2 indicates the number of moles. Means X2, number of moles of X2 divided by N1 plus N2. Here N1 plus N2, again these are the number of moles of solute and solvent. So this mole fraction, if it is X1, then this equation will be N1 divided by N1 plus N2. If this is X2, this equation will be N2 divided by N1 plus N2. This N1 plus N2 means these are the number of moles of solute plus solvent, and totally it is called as number of moles of solution. That's why it is written here, mole fraction of a component of a solution is equal to its moles. X2 के मोल से ये N2 divided by the total moles in the solution. Total moles in the solution means the number of moles of solute plus number of moles of solvent here. So X2 is very important. Where this N1 and N2, N1 and N2 is where N1 and N2 is the moles of solvent and solute respectively. If N1 and N2, these are the moles of solvent and solute respectively. Remember, N1 is a solvent and N2 is solute, but these are the number of moles. We are dealing with the dilute solutions. So dilute solution means number of moles of solvent will be very, very high. So this N1 will be very, very high. For the dilute solution means solvent is more. So N1 is very, very larger than N2. So N1 plus N2 is equal to N1, because N1 is number of moles of solvent. And for dilute solution, number of moles of solvents are very, very large. So N1 is very much greater than the N2. So this N1 plus N2 is equal to N1, because this number of moles are more. So the mole fraction is given, mole fraction, X2 is equal to N2 upon N1. N2 upon N1, because N1 plus N2 is equal to N1. Why? Because the number of moles of solvents are very, very large amount. So this is considered as N1. So this expression becomes N2 divided by N1. N2 divided by N1. And this equation 2.8, X2 is N2 upon N1. So delta P upon P naught 1, putting this value N2 divided by N1, putting this value in this equation. See, we know delta P upon P naught 1 is equal to X2. So what is X2? I am putting this value of X2. X2 is N2 divided by N1. So this equation 2.8 becomes this equation 2.9 by putting the value of N2 and N1. So if you prepare the solution by dissolving, this is a W2 grams of solute. W2, this is a mass of solute. W1 is a mass of solvent. By knowing this mass of solute and solvent, we can calculate the number of moles. So N2, already N2 is solute. So N2 is equal to number of moles. So what is the formula of number of moles? Mass divided by molar mass. So W2 is the mass absolute and M2 is the molar mass absolute. Here W1 is the mass of solvent and M1 it is the molar mass of the solvent. So putting this value N2 and N1 in this equation, in equation 2.9. Once again, I am explaining this N2. These are the number of moles of solute. W2 is the mass of solute. M2 is the molar mass of the solute. N1, this is N2 is solute and N1 is solvent. So N1 is the number of moles of solvent is equal to mass of solvent divided by molar mass of solvent. Don't get confused between which is solute and which is solvent. Clearly it is shown here N1 is solvent and N2 is solute. And the number of moles, the formula is mass upon molar mass. Whether it is a solute or whether it is solvent, the formula it is same. So putting these values N2 and N1 in this equation, so we will get only we are putting this N2 and N1 value. See N2 and N1 value in this equation, and so delta P upon P01 is equal to N2. N2 means this W2 divided by M2 we are putting. So these values delta P upon P01 is equal to N2. N2, this is a W2 upon M2. This is the value of N2. W2, you know, this is mass and this is molar mass. So N1, this W1 is mass and M1 is molar mass. So by rearranging this equation, we get same equation is there. Delta P upon P01 here is also delta P upon P01 is equal to this expression, you know, P01 minus P1. This is a relative lowering of vapor pressure. This is a delta P upon P01 is already relative of lowering vapor pressure and is equal to W2M1. See, W2M1 means when this is shifted to upper side, it will be multiplied. So W2 into M1 and M2 into W1. This equation 2.11 is very important for solving the numericals. So we are derived the relation between molar mass of a solute and vapor pressure lowering. See here delta P upon P01 is relative lowering of vapor pressure and molar mass of a solute M2. See this M2 by knowing the values of W2, by knowing the values of this M1 and by knowing the values of this W1, we can calculate this M2. So this expression many times it is asked for board exam for 2 marks. Remember this expression delta P upon P01. This is a expression of relative lowering of vapor pressure. Vapor pressure lowering is delta P. Delta P upon P01 is relative lowering. P01. Now remember, P01 is the vapor pressure of pure solvent. P1 is the vapor pressure of the solution containing non-volatile solute. What is this N2? Number of moles of N2 is number of moles of solute. Then N1 is number of moles of solvent. If these concepts are clear, we can derive this any expression. So this is a physical chemistry part. Make a practice at your home, at least solve this expression for 2 times or 3 times. Then it will be very easy because numericals are also asked on it for 3 marks or 2 marks or 1 mark. Numericals are also there. So I have given the numericals also here. We can solve the numericals at your home because these are very solved numericals, very simple numericals. Only the calculation part is there. Only put the values, and this numerical is the value of numerical is wrong. That's why I have corrected this numerical number. Remember which is a number 2.5, I think. So in your textbook there is a mistake. in the numerical, so I have corrected it. So problem number 2.5 I have solved. This is a handwritten photographs I inserted here. So we can solve this problem number 2.5. Just we will solve. I will take one example. The solution is prepared by dissolving 394 grams of non-volatile solute. See, it is clearly indicate here non-volatile solute is given, means it is a mole fraction. Sorry, non-volatile solute means it does not contribute to the vapor pressure. 394 grams of non-volatile solute in 622 grams of water. Water is a here pure solvent, and this 394 grams of non-volatile solute is added. Then the vapor pressure is given. The vapor pressure of the solution is found to be 30.74 mmHg, and the temperature is given at 30 degrees Celsius. If vapor pressure of the water is 30 degrees Celsius, and this is the this is the vapor pressure is given. Vapor pressure of water is given, and what is the question is asked? What is the molar mass of the solute? We know this expression already. We derived delta P upon P naught 1. This is the relative lowering of vapor pressure, and this is a W2M1. This is the relation between molar mass of a solute and relative lowering of vapor pressure. Means here in this equation we have to calculate this molar mass. M2 we have to calculate here. So we have W2 is given. W2 is mass of the solute is given. Non-volatile solute is given 394. W1 is the mass of the solvent is given. Clearly see here W2 is what? 394 grams. See, mass of the non-volatile solute is given. W1 is 610 to 2. This is the mass of the yes, 622. This is the mass of the water, means mass of the solvent is given. M1 is the molar mass of water, because it is not given, but we have to calculate this. H2O means hydrogen is 1, 2 hydrogens 2, and oxygen is 16. 16 plus 2, 18 grams per mole. So this is expected from the student. It is not given. Molar mass of water we have to calculate. M1 is equal to 18. Then P1. P1 is given here in this equation. See, the vapor pressure of the solution is given. Means this P1 is the vapor pressure of the solution containing non-volatile solute is given 30.74 mmHg, and this is the vapor pressure of the pure solvent. So vapor pressure of the water is also given. All the values are given. Only we have to put in this equation, and we have to calculate M2 only. So we have to rearrange this equation. All these values are given, and only we have to put in this equation, and we have to solve. We will get the answer 342 grams per mole. This is a 3 marks numerical, remember. This is a 3 marks numerical. 1 mark is for this formula, 1 mark is for putting these values, and 1 mark is for calculation. So if you at the time of board exam, if you written the formula, if you correctly put the values, we will get these 2 marks, and if you didn't calculate, you will lose your 1 mark here. Means numericals, for solving the numericals formula you should know what is given. If you finding the difficulties